Hello, in this video we're going to look at the binomial probability distribution. So a binomial probability distribution, which can be represented as shown here, where I have a random variable x, and then we use b and np. So n and p are going to be the defining parameters for a binomial distribution. This applies when we have an experiment repeated n times. Only two outcomes are possible, success or failure, and we consider p as the probability of success. And these don't have to be equally likely outcomes, and I can have an experiment in which multiple outcomes are possible, but they are grouped into two categories, success or failure. And outcomes are independent of each other. So in other words, at each trial, at each repetition of the experiment, the probabilities do not change. So we have the probabilities don't shift. It's p the whole time for all n repetitions of the experiment. When I'm then trying to figure out the probability of a certain number of successes within the overall set. So that probability is given by the formula down here. The probability that the random variable will take a particular value x is, now this involves a combination. So ncx, which if you will recall is n factorial over n minus x factorial, and I'll explain why that's there in a moment. The part that maybe makes a little more sense is why we would have p to the power of x and 1 minus p to the power of n minus x. So if, for example, I have 10 repetitions of an experiment, so 10 trials, and let's say we have the probability of success is 0.75 each time. If I want to know the probability of, let's say, 3 successes, let's go with 7 successes because that's closer to what our probability actually is. If I want to know the probability of 7 successes, think, well, each success has a probability of 0.75, and since they're independent, we multiply probabilities together. So the probability of a success multiplied by the probability of another success multiplied by the probability of another success, etc., 7 times. But if I have 7 successes, I also have 3 failures. So 1 minus p would be the probability of failure, and that has to happen 3 times. Now, the reason we need the combinations calculation in there is essentially because we have a number of different ways in which these successes and failures could happen. For example, I could have 7 successes right up front, followed by 3 failures. Or I could have a success and then a failure, and then a couple more successes, and then 2 failures, and then 4 more successes. There's a bunch of different ways in which these probabilities can happen, and each of them is a different 0.75 to the power of 7 times 0.25 to the power of 3 probability. So the number of ways this can happen needs to be multiplied by these probabilities. So that's where the NCX comes in. So in this case, that would be 10 trials and 7 successes. So we can calculate it that way. Now, that is the formula that's being used. So if I consider an example here where we have Ben shooting at a target 10 times with a probability of 0.7 of hitting the target with each shot, and we're assuming that over the course of these 10 trials, his probability of success doesn't increase or decrease appreciably. In reality, we know that over time that would shift, but we're in a, I guess, defined enough period here that the probability shift is not going to be significant. So what's the probability that he hits the target with exactly 7 of his shots? Would be 10C7. For the number of, I guess, ways those shots could be ordered. Is it hit, miss, miss, hit, 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 miss, etc. Times the 0.7 to the power of 7 times the 0.3 probability that he would miss to the power of 3. So if we deal with that, then what I get when I calculate this is that probability is about 0.267 when I round it to 3 significant digits. Now the difficulty comes, and just as a side note, I can use this formula every single time, but most calculators will actually have the ability to just input n and p. It will have a binomial probability distribution calculated or programmed into it. On the TI graphing calculators, that looks like binom PDF. In the Casio graphing calculators, if you go into the stats menu, you get binom PD without the F. The F just stands for function, but binomial probability distribution. In the Casio, that's in, like I said, the statistics app. And on the TI, it's in the distribution menu. You can scroll down and find binomial PDF. Now, you then would input the number of trials and the probability and the X value that you're looking for. So I have 10 probabilities. I have my probability of success, and I'm looking for 7 successes. What's the probability that he hits the target with less than 7 of his shots? Well, this actually is the probability of 0 successes or 1 or 2, etc., or 6, because less than 7 does not include 7. And for this, I mean, that's 7 separate calculations I would have to do using the formula or using binom PDF. For this, we can actually use the binomial cumulative. So binom CDF is what it is called on the TI calculators, or binom CD on the Casio calculators. This is essentially the cumulative probability distribution and function if you have the TI. So what I can do for this, the probability that X is less than 7 is going to be the sum of all the probabilities. So 10, let's say I, CI, 0.7 to the power of I, 0.3 to the power of 10 minus I, for values of I going from 0 to 6. In my calculator, I can choose binom CD, which is going to calculate all the probabilities cumulative up to a particular maximum. So the X value I'm going to use there is going to be 6. I'm going to tell it the maximum number of successes I want to include is 6, still with 10 trials and a probability of success of 0.7. So this now is going to add up all of the probabilities up to 6, and it gives me a probability of approximately 0.350 to 3 significant digits. On the calculator, your CD, your cumulative distribution function, is always going to be a left-hand cumulative. So it's always going to be from 0 to the value that you give it. It's always going to be the less than. If I want to know something bigger, so what is the probability that he hits the target with at least 7 of his shots? So that means 7, 8, 9, or 10. In other words, the probability that X is greater than or equal to 7. Then I can use the cumulative probability, but I have to note that the cumulative probability is for less than. So this is going to be 1 minus the probability that it is less than 7. So in this instance, because I've already calculated that that's 0.35, the probability that he will hit at least 7 is going to be the complement of that, so approximately 0.65.